Have you ever stopped to think about this? Your computer's brain is just screaming fast, right? Billions of operations a second. How does that talk to something as slow and clunky as your keyboard? It's a really fundamental problem in computer architecture, and today we're going to dig into how they solved it.
Okay, let's dive right in. I mean, this is really the central question, isn't it? You've got a processor and memory that are unbelievably fast. And then you have everything else. Your printer, your mouse, your hard drive, which in computer years are moving at a snail's pace. So the big question is, how do you get them to communicate without the super fast parts just sitting around twiddling their thumbs waiting for the slowpokes to catch up? So to get to the bottom of that, we've got to first understand why this is even a problem in the first place. I mean, why can't you just, plug a keyboard straight into the computer's main data highway? Turns out there are some really, really good reasons why that's a terrible idea.
The thing is, the world of peripherals, it's just a total mess. You've got your hard drive speaking one language at a certain speed, and your keyboard speaking a totally different one, way slower. Some devices send these tiny little trickles of data, while others are blasting huge chunks. But the biggest deal, they are all incredibly, mind-bogglingly slower than the CPU and memory. Trying to connect them directly? Yeah, that's like telling a Formula One driver they have to stay in first gear and follow someone walking down the street. It's a complete non-starter.
So, what's the fix? Well, this is where the hero of our story comes in, the I/O module. Seriously, this thing is a brilliant piece of engineering. It's designed to solve this exact communication nightmare. Think of it as a UN translator, a diplomat, standing right in the middle of these two completely different worlds.
And this picture here, it just lays it out perfectly. See that I/O module? It's sitting smack dab in the middle. On one side, you've got it hooked up to that super fast system bus where the CPU and memory are chatting away. And on the other side, it's got all these connections going out to your printer, your mouse, you name it. It is the ultimate middleman.
So if we're getting a little more formal about it, an I/O module is a specialized little unit with its own logic. It's got its own brain, in a way, and its entire job is to manage this flow of information. The key thing to get here is that it's not just a dumb plug adapter. No, it's an active manager. It's the thing that makes this whole Rube Goldberg machine actually work together.
And wow, does it have a lot of jobs on its plate. It's juggling control signals and timing, it's talking to the processor, it's talking to the specific device, it's buffering data to kind of smooth out those crazy speed differences, it's even doing error detection. Like when your printer has a paper jam. The I/O module is what figures that out. At the end of the day, it's taking this huge administrative burden right off the CPU's shoulders.
Okay, so how does this all work in the real world? Well, over the years, engineers came up with a few different ways to handle it. Let's look at the evolution. The very first, the simplest method they came up with was called programmed I/O.
I like to call this the babysitter method. It's pretty easy to picture. The CPU basically tells the I/O module, hey, go get me a keystroke from the keyboard. And then it just sits there, constantly nagging it. Are you done yet? Are you done yet? How about now? Got it yet? It's not very efficient.
When you break down the steps, the inefficiency is just glaringly obvious. The CPU issues the command, and then it gets totally bogged down in step 2, just waiting and checking, over and over. It can't do any other useful work. For a powerhouse like a modern CPU, this is just an unbelievable waste of potential. And this flowchart here really drives the point home visually. You see that check status loop? That's the trap. The processor is literally just spinning its wheels, running in circles, asking, is it ready? Is it ready? Again and again. What a terrible use of a brain with billions of transistors, right?
So yeah, clearly that couldn't last. There had to be a better way. And there was. The next step in the evolution was a much, much smarter approach. Interrupt-driven I/O.
This one I call the pager method. Think about it. The CPU gives the I/O module its task, and instead of waiting, it says, all right, you got it, just page me when you're done. And then it goes off and does a bunch of other useful work. It's only when the I/O module actually has the data ready that it sends a little signal. That's the interrupt, to tap the CPU on the shoulder and get its attention. And just like that, the whole process is transformed. The CPU issues its command, and boom, it immediately switches to another task. It stays productive. Then, when the I/O module is finally done, it sends that interrupt signal. The CPU just pauses what it was doing for a split second, deals with the data, and then gets right back to where it left off. It's just so much more efficient.
If we go back to our flowchart, you can see the magic happen right here. That annoying waiting loop, gone. It's been replaced with this beautiful new path that says, do something else. The CPU is finally free. This was an absolutely massive leap forward for computer performance. But there was still a small problem. For really big chunks of data, we're talking about reading a huge file from a hard drive or something. Even interrupts could be a bit of a drag. The CPU still had to get involved with every single little piece of data. So that led to the final, most powerful technique of all, direct memory access, or as everyone calls it, DMA. This is the delegation method. It's the ultimate form of management. Now, the CPU acts like a smart CEO. It doesn't just tell a manager to get some data. No, it goes to a specialist, the DMA controller, and says, listen, I need you to move this entire block of data from point A, the hard drive, to point B, this spot in memory. Don't bother me with the details. Just let me know when the whole thing is finished.
This is a total game changer, and here's why. The CPU's involvement drops to almost zero. It issues one single command right at the beginning, and that's it. It goes back to its real job, crunching numbers and running programs. Meanwhile, the DMA controller handles the entire transfer by itself, directly with memory. It only bugs the CPU with one single interrupt when the whole massive block of data is safely transferred. Incredible.
And our third flowchart here, it just tells the whole story perfectly. The CPU just fires off one command and it's free. All that messy, complicated work of moving data, it's all handled by the DMA module. This is pretty much the peak of I/O efficiency.
So now, let's put all three of them side by side. When you do that, you see this beautiful story of evolution. On the far left, you have a CPU that's literally trapped, running in circles. In the middle, you have a CPU that's been freed to do other things, but it's still getting poked for every little piece of data. And then, all the way on the right, you have the master delegator, a CPU that hands off the entire job and only gets one single tap on the shoulder at the very, very end. The goal through all of this has always been the same. Let the CPU do what it's best at, which is compute.
Now, it gets even more interesting because even DMA has a few different ways it can be set up. The first and simplest way is to have a separate DMA controller sitting on the main system bus. It gets the job done, sure, but it's a little clunky. Why? Because the data has to travel on that busy system bus twice for every transfer. It creates a lot of extra traffic, kind of like a package having to go back to the main sorting facility before it can go out for delivery. So a much smarter design is to integrate the DMA controller right into the I/O module itself. And you can see here the improvement is huge. Now, that data only has to hop on the main system bus one time to go straight from the I/O module into memory. It's so much cleaner, so much more efficient. But the most sophisticated systems, the real high-performance stuff, they take it one step further. They build a completely separate I/O bus. The analogy here is perfect. It's like building a dedicated service road just for all the I/O delivery trucks, keeping them completely off the main superhighway where the CPU and memory are flying back and forth. This just crushes congestion and lets the processor and the DMA do their things at the same time, with maximum efficiency. So there you have it, from the annoying babysitter to the pager, all the way to the master delegator. This incredible 50-year evolution is the hidden reason why our computers feel so snappy and so instant today. It's the silent, invisible dance of cooperation happening billions of times every single second inside your machine. And it really makes you wonder, doesn't it? What's the next great communication bottleneck going to be? And what kind of genius solution are engineers going to come up with to solve that?